So we have actually covered all the fundamental concepts. So that's the first module of 16100. And we'll come to incompressible potential flow today. And we'll cover potential flow theory, right? So that's what we're going to do today. And starting on Wednesday, we'll apply potential flow theory on airfoils. Once we have a potential flow theory on airfoils, we can start to analyze aerodynamic stability. Okay, and after that, we'll generalize our potential flow theory to 3 dimensions, which is going to look more quantitatively at lift-induced drag, which we already looked at in the fundamental concepts. All right, but more qualitatively. Now we are getting quantitative. During this, there is a quiz, like the first quiz of 16100 that covers basically everything up to this point. And the current schedule is going to be next Wednesday, not the immediate Wednesday, but the Wednesday next week. All right, yes?
It's during class.
During class, yes. All right. And after the incompressible potential flows, we'll do viscous and compressible flows. Okay. And that's going to cover more stuff like high lift airfoils, transonic and supersonic flight, and viscous boundary layers, shocks, etc. After that is followed by quiz 2. And after quiz 2, we'll get into the team design project. All right. So hopefully the scheduling of the quizzes kind of avoids midterms and final exams of other subjects, right? So that I think this happens way before midterm of other subjects, and this is usually between midterm and final. So yeah, the time hopefully works well for you guys. All right, any questions on that aspects? No? Okay, so let's get into our second module, incompressible potential flows. The first thing I want to get clear is the answer to this question. And I want you guys to think about yes or no, and why is that? Is the sum of, let's just consider 2 steady state flow fields, right? So we have one steady state flow field that's all valid, right? Satisfies conservation of mass, conservation of momentum, conservation of energy equations. You have a second steady flow field that satisfies exactly the same set of equations. Now I add them up. Is the new flow field still a valid flow field? Meaning, does it still satisfy conservation of mass, conservation of momentum, conservation of energy equations? Yes or no? Yes?
I'm leaning towards yes, I would say.
Okay. And you have any idea of why you are leaning towards yes?
Yes, like let's say you have one that's purely in the x and one that's purely in the y. If you add them together, you get another straight flow field. You should have a kind of tendency.
All right, so you're giving an example that is actually a perfectly valid example. If I have a one flow field, U1 is equal to, let's say, A, okay? Let's say V1 is equal to 0. That's a flow purely in the x direction. And you have a U2, another flow field that's purely in the y direction. Then the sum of these 2 flow fields would be U equal to A, V equal to B, right? That's a perfectly valid flow field. And in both flow fields, because the flow is just goes along either in a single direction, the pressure is what? What's the pressure field like for both of these flow fields? Uniform, right? So the new flow field also have uniform pressure. So this is a case where the sum of 2 flow fields is still a perfectly valid flow field. Well, the real question is, does this very simple example generalize? And if so, to what extent it generalizes? Anybody have any other thoughts? Does everybody agree, like, if you add up 2 flow fields, you get another flow field. Anybody disagrees? I mean, you don't have to construct a counterexample. Maybe you can just think of any reason it might not be true. Oh, I will tell you the answer. I mean, this does generalize, but only to a certain extent. Right? There are definitely cases for which the answer is not true. Any idea why? Yes? Two flow fields in opposing directions. Yeah, thank you for saying that, because otherwise I couldn't continue. So if you have u1 equal to a, v1 equal to 0, you have u2 equal to minus a, v2 equal to 0. If you add them up, what do you get? U is equal to the sum, v is equal to the sum, right? That seems still a valid flow field. But like, thank you for saying that, because yeah, let's keep trying. I said it doesn't have to be a counterexample, right? It's not actually easy to construct a counterexample, but there are, yes?
Could it be if like the two different flow fields were in like different regimes, so one was like incompressible and one was compressible flow?
Yes. How about two different flow fields in two different flow regimes? Why do you think that'll actually create something that doesn't work?
I just think like with compressible, we use different like interactions with like formula versus compressible. They're like two different formulas, so I feel like they wouldn't interact well. It's just adding. Okay, that's actually a very good reason. Because if you have things that, so I mean, mathematically, right? What kind of things add together nicely? What kind of things doesn't add together nicely, right? So if you have two equations in general, if you have an equation in general, and the two solutions of the same equation, in what cases would add up to another solution to the same equation? Any previous experiences in mathematics? Huh? Yes? Yes, linear equations exactly would have two solutions adding up to also another solution. Right? Okay, let me just give you an example, right? X plus y equals to 1. All right, x plus y equals to 1. One solution is x equal to 1. Oh, actually, no. X plus y equal to 1 is not a linear equation. So x equal to 2y. All right. X equal to 2y. If you have one solution, x equal to 1, y equal to 2. No. X equal to 2, y equal to 1, right? Another solution, x equal to 4, y equal to 2. You add them together, x equal to 6, y equal to 3. It's a perfectly valid solution. So this is the kind of linear equations that makes the sum of two solutions also a solution. Now, are the conservation of mass, momentum, and energy equations linear equations or not linear equations? Yes or no? Well, let me just remind you what are the conservation of mass equations. For steady state flow fields, right? So we just get rid of the partial t term. And the conservation of mass equation would be, and also let's just assume it's incompressible, because that makes things a lot easier. So we can pull rho out of the derivatives. Rho has a tail, partial u, partial x, plus partial v, partial y is equal to what? Conservation of mass. The integral of rho and then v dot n.
Right, so this is the divergence of velocity. If you integrate the divergence of velocity over volume, you get a surface integral, right, of all the outflux of velocity, which has to equal to what for the flow field to be steady state? 0, right? That's how it derived the conservation of mass equation. I think I didn't derive it. Our TA derived it in the first recitation, right? So if you integrate this over volume, it is equal to total outflux, right? For steady state, you cannot have the mass inside the volume to keep decreasing in a steady state, right? Mass is going to eventually become negative. That's impossible. So this has to be equal to 0. Is that a linear equation or not? If you only consider the velocity field, is that a linear equation or not? If you have U1 V1 satisfying this equation, you have U2 V2 satisfying this equation, you add them together, does it still satisfy? Yes, right? Please say that. Because derivative is a linear operator. The derivative of the sum of two functions is the sum of the derivatives. Okay, good. So this is linear. How about conservation of momentum equation? Conservation of momentum equation is, again, let's just write for incompressible flow. So rho times u times du dx plus v times du dy, so that's the momentum in the x direction, plus dp dx is equal to 0, right? Equal to 0 because I'm assuming inviscid, and also in the y direction, it's rho times u times dv dx plus v times dv dy. Now, because it's in the y direction, I'm looking at the pressure force in the y direction, which is the pressure gradient in the y direction, equal to 0. Now, is that a linear equation or not? If I have two solutions, let's just focus on the first equation. If I have two solutions to the same equation, do they add up also satisfying the same equation? Yes or no? No, right? Why no?
I think it's because you're multiplying by the unit of the u, so it's like you have the du times the u, so it's not really just you're not multiplying by a constant.
Yes, there is what we call a quadratic term over here, right? The linear equations usually has a very nice property in the sense that if you double something, doubling something is adding something by itself, right? If you double a quantity, you get double the outcome, right? So du dx, for example, if you double u, you get twice the du dx. Here, if you double u, you get 4 times the du, 4 times the first term, right? It doesn't work. So just like y equal to x squared is not a linear equation. If you have one set of solutions satisfying y equal to x squared, y equal to 1, x equal to 1, another solution y equal to 4, x equal to 2, you add them together, y would be equal to 5, x would be equal to 3. It doesn't satisfy anymore, right? Okay? So this is not a linear equation. But why did all these examples work?
There is no dependence on x or y.
Yeah, these examples work because these all are 0, right? 0 is also trivially satisfied, right? So basically, in order to construct the counterexamples, we need more complex cases. More complex cases. Okay, so there are actually a lot of cases where the sum of two flow fields is not equal, does not satisfy the equations. But today what I want to tell you is that through some very lucky coincidence, these equations are automatically satisfied for incompressible and potential flows. Okay, which means if I construct a particular pressure according to Bernoulli's law, right? So for whatever flow field that is incompressible and potential flow, which means vorticity is equal to 0. Okay, incompressible means this equation is satisfied. du dx plus dv dy equal to 0. Potential flow means vorticity is equal to 0. That means du dy is equal to dv dx, right? I mean, another equation. If both are satisfied, then you just substitute a pressure is equal to a constant minus half of rho u squared plus v squared, right? The standard Bernoulli's equation. Then these two equations are automatically satisfied no matter what. So when you're answering this question, right, is the sum of two steady state flow fields still a steady state flow field? You don't need to consider this equation at all, because as long as the sum of the two flow fields satisfies this equation, you know I can construct a pressure field that's just according to Bernoulli's formula that makes these two equations satisfied. So the only question is the sum of two flow fields still incompressible, still satisfies this equation? Is the vorticity of the sum of the two flow fields still 0? The answer is actually yes, right? Because vorticity is also linear with respect to velocity. If I have one flow field that has du dy plus du dy equal to dv dx, another flow field du dy equal to dv dx, then the sum would also satisfy du dy equal to dv dx. Okay, so that means the answer is yes for incompressible and the potential flows. And that is why it's actually pretty hard to construct an example that the answer would be no, right? Because, well, these are two incompressible potential flow fields. These are two incompressible potential flow fields that actually satisfy these equations. And these equations would be this equation, and another equation would be du dy has to equal to dv dx. And why is the conservation of momentum equation always satisfied? So let's just take the first equation as an example. All right, let's take the first equation as example. This is because if I substitute the pressure is equal to just the arbitrary constant, let me just take the constant to be 0, then my pressure would be half of rho times u squared plus v squared, right? I mean, any constant would not change this equation at all because I'm taking derivative. All right, then if I substitute the p equal to that, then what is dp dx? Then dp over dx would be equal to, let me just pull rho out of the derivative because it's incompressible flow. And the du squared dx would be 2u times du dx, right? The 2 always cancels with the half. So what you get is u times du dx plus v times dv dx, right? Now, dv dx is equal to what according to the assumption that vorticity is equal to 0? right? dv dx is equal to du dy, right? So v times du dy. Now you substitute this dt dx into this equation. It's exactly the same as the first term, except for there is a negative sign. So for that pressure, right, things automatically cancel out. And you have automatic satisfaction of the momentum conservation equation. And it doesn't matter it is nonlinear. All right? Okay, so what does this mean? This means for incompressible potential flows, we get this incredibly nice property that if you add two flow fields, you get another valid flow field. That means we can just add up different flow fields to make up various more and more interesting flow fields. And this is practically what we'll be doing for the entire week, right? Adding up flow fields to make up new flow fields and look at what kind of, to make up a more and more interesting flow field that approximates what actually happens around different airfoils at different angles of attack. Okay, so just to give you one example. This is a perfectly fine flow field, right? And another, I mean, it's incompressible and potential. I'm sure like you're working on your homework, and in your homework, you get this vortex flow field, right? And that's another incompressible potential flow field. How about add them together, right? That's actually something you're working on in your first homework problem, right? And I'm sure you worked out the formulas and stuff, but like, have you ever thought of what the flow field actually look like? You did? Can you describe it?
It's the one vortex turning that way and the other turns that way. It's like net going down.
Oh yeah, that's the first question or the second one? The second one. Yeah, I'm asking the first one.
I don't remember that part too well.
Oh, it's basically a free stream, I think U infinity, V infinity plus a vortex. Right, so one is just a uniform flow field, the other one is the vortex. Anybody thought about what the flow? Yes?
Should a vortex moving in the direction of the free stream?
The vortex moving in the direction of the free stream. Actually, okay, so that's actually a good point in the sense that the vortex is actually not a potential flow on the point of the vortex, right? So if you add up the flow fields would not be a steady state flow field exactly on the vortex. So you kind of have to think about the flow as the flow like around this vortex, not the flow at the vortex. So at the vortex, if you actually solve the equations, it has to be unsteady because the vortex would have to move along with the flow. Okay, but if you focus on the flow around it, it could be steady state. So what would the steady state flow look like? Think about it. It looks like something like this. Right? It's something a lot more interesting, right, than just either free stream or just a vortex, right? If you have a vortex, it just rotates. You get circular streamlines. If you have a free stream, you just get linear lines, right? For a free stream plus a vortex, you get this interesting stuff. Actually, these would be the streamlines. And then you also get a closed body, something like a teardrop shape, in which the flow just goes around it without going out of it. And the flow outside goes like this, and you can also read the flow field, right? Whenever you have the shrinking stream tube, you know the flow is accelerating, right? So you know the flow velocity is probably quite high over here. I mean, this is a visualization of if I seed some particles upstream, where this particle goes.
So here you can also see these particles are spread pretty far away from each other. That means the flow velocity is quite high, right? You can also see it from the tube, stream tube shrinking to very small. While on this side, right, the stream tubes are very far apart. That means, and also a lot of particles are concentrated over here. So that means like the flow velocity is pretty low up here. And also it's potential flow, right? So we have Bernoulli's not only along streamlines but across streamlines. That means you know the pressure here is what? Very low, right? Because the flow is very fast. The pressure here is quite high, right? Because the flow is almost stagnating. By the way, this is actually something you can think about this as the flow around an airfoil like this at minus 90 degrees angle of attack. If we can somehow magically prevent the flow from separating on the backside of the airfoil, right? I mean, like an airfoil would never stay attached at 90 degrees angle of attack. I mean, at least with today's technology. But if we can, the flow field would look exactly like that. So this is a single vortex, right? We can add more. We can add more stuff. We can add two vortices, and the free stream plus a vortex plus another vortex would still be a perfectly valid flow field, right? So that's why I have this website that you can go to. Let me see. So that's the website. It's called chichi.github.io/flowbuilder2. That you can basically add as many stuff as you want and see what the flow field is like. So this is the same flow field as we are seeing on the slides. And if you can just click on the flow field, you can see the additional particles. For example, if you see a lot of additional particles inside this region, you can kind of visualize how this kind of airfoil at minus 90 degree angle of attack is like. All right, you can start to see this solid shape. And as I said, the flow field near the vortex would not be a physical flow field, right? Because here the vorticity is not zero. You are adding two flow fields. It doesn't satisfy the momentum equation. But if this is actually a solid body, then the flow outside of it are completely fine, right? They satisfy all the equations you want. That's actually the basic strategy we are going to be taking to study what the flow field is like around solid objects. That is, we try to place vortices inside the solid body, not outside of it, right? Inside the solid body, so that we are going to match the contour of the solid body with the tangential direction of the flow field. And that actually gives us what the flow field is like around the solid object. Okay, and using Bernoulli, we can also see what's the pressure distribution like. And in this case, we see this airfoil get a huge negative lift, right? So the lift is going to be towards this direction. Because why? The pressure here is high. The pressure here is very low, just the Bernoulli's. Right? The streamlines are so narrow over here that the flow velocity must be very high and the pressure must be very low. And you can move your mouse to here and see, right? The pressure here is like minus 6.94. And by the way, the unit are the following. The pressure at free stream is set to be 0. So if you move far away, you get pretty much 0. The pressure at stagnation point, I mean, the pressure is basically computed as the difference between the pressure here, which is minus half of u squared plus v squared, density is assumed to be 1, right, minus the pressure at free stream. So that's what this number is. That means pressure equal to 0.5 would be a stagnating pressure, right? Because the U infinity, V infinity is equal, U infinity is equal to 1 here. Okay, so P equal to 0.5 would be the flow decelerate to completely standstill, right? So here it's pretty close. And over here it's pressure is very low, so you get the really high suction, right, downward. That's lift, right? Because the free stream goes that direction, force perpendicular to the relative direction of motion, that is lift. All right, any questions regarding that flow field? Okay, and just to give an example, right, you can duplicate this. That's another vortex. You can make it minus 100 if you want. I mean, that actually cancels everything out, but you can move this thing to, let's say, 300. That actually creates something like a contraction, right? And let me just start to asking questions regarding to this type of flows, right? Because now we know that we can actually construct different scenarios by just placing different vortices. 1 second. Okay, so let me, anybody know who this guy is? He founded, one of the co-founders of Skunkworks, and designed something like 40 airplanes, and quite influenced. I mean, these aircrafts actually quite influenced how the Cold War unfolded. And this guy has to turn down the presidency of Lockheed Martins for like at that time it was still Lockheed, for 3 times. And his boss once exclaimed, this person can actually see air. Huh? Yes. I mean, these are the kind of airplanes he designed. Right? Do you know what these airplanes are? I mean, the bottom ones are more famous. SR-71, right? That's F-117, and that's the U-2. Right. So this guy actually pretty much designed all of these airplanes, and so. Today we actually going to see like if we can train you to also see air. All right. That is basically what we are trying to do here. That's kind of start to use the principles we have learned in the fundamental part and use the idea that you can basically superimpose different flow fields to come up with new flow fields. So for example, this is actually a case that's very similar to what we just did, right? We just put 2 vortices, like plus a free stream, and we actually created. So imagine the flow, right? Because we know the flow around these points are not physical, so we have to look at the flow that's not including this point. So basically, we have to put a solid boundary that protects these points. So in this case, the solid boundary would be a tube that's contracting and then becoming wide again, right? That's a Venturi tube. Okay? So let me see if you can answer this question. Now you can think about the flow field as uniform flow field plus a vortex sitting here plus a vortex sitting here, right? Now you can start to visualize what the flow field is composed of in terms of elementary building blocks. I want to ask if a flow particle is released at a quarter height, so basically a quarter of the height. I don't know if this is the number of arrows doesn't work well, but like a quarter height is roughly over here. Okay, it goes through this. Where is the particle when you're at station 2?
Quarter height.
A quarter height? Why?
Makes sense. Then going back to GitHub thing that you showed, like the particle that started low, like also entered low again.
Yes, if you think about the flow field like two vortices, the flow field is completely symmetric on this side and that side, right? It's completely symmetric. So whatever happens over here is almost an image of what is happening on that side. Agreed? So a part of a flow streamline that started over here would basically end at the same position on the right-hand side. So very good, thank you. Now the more difficult question, how about at the throat over here? Is it above a quarter or below a quarter height of this throat? Yes? No, anybody? Huh? At a quarter height, why?
Again, it's compresses the volume compresses, but also the air compresses with it. So it's just keep going at quarter height the whole.
Okay, so I think you touched a key point, is that you said the stream tube compresses and it compresses equally, right over here. So what makes you think that it compresses exactly equally? So that's a very good point, because the fact that whether it compresses equally or not, right, determines where this point is. If it, for example, if it compresses more at the center, then that particle would be closer to the center, which means it's above the quarter height. If it compresses less at the center and more near the two sides, then the streamline would be closer to the boundary than a quarter height, right? So that's a very good step in the thinking. But is it compressed equally? Yes?
I don't think so. That's a boundary layer effect. Virtually the wall.
Boundary layer effects. That's actually correct, but let's just think about incompressible flow. Sorry, inviscid flow, potential flow for now. So that imagine just the boundary layer is very, very thin. Okay. By the way, in a realistic case, the boundary layer would be very thin over here. I mean, that's actually, remember the wind tunnel tour, right? Why do you think they make a contraction when the test section is over here? It's to make the boundary layer thin, right? Because in the test section, you don't want a thick boundary layer. And we will study that in the viscous flow section, is that when you go from here to here, you have a very favorable pressure gradient. The pressure decreases from here to here. That thins out the boundary layer. But over here, the boundary layer might be pretty thick because you are at the adverse pressure gradient. That thickens the boundary layer. So your concern would be a perfectly valid concern over here. Because of the boundary layer, the location of that particle may not be quarter height over here. But over here, the boundary layer is much less of a concern. All right. Now, assuming there is no boundary layer, perfectly potential flow, right? Is the particle above or below a quarter height? Let's take a look. It's too close together. So let's make this 460 and 200, maybe a little bit better. So let's wait for the things to become more steady state. I mean, the flow is always steady state. It's just the particles, they are initially at the low. I mean, they are initially not in streamlines, right? Is it compressed equally? No, right? Where is it compressed more? At the center or at the two sides? At the sides, right? The center seems to be compressed the least. And why? Why do you think is that the case? Yeah?
Like the flow in the middle can just travel straight through, but when it's coming from the walls on the side, it has to compress, it has to travel a lot further, like vertically.
It has to travel a lot more vertically.
So I guess if you look at the flow, like starting in the center, like halfway up,
Uh-huh.
it wouldn't really have to move at all. It can just travel like straight.
Yeah, this can travel straight. Okay, yeah. yeah, this has to move down. But why would the stream tube contract more if it has to move down? Yes?
I also think like when you add the two vortices together, when you kind of get to the center, they're not like really like opposing each other as much anymore. Whereas like when you're just really close to like the bottom one, for example, it's like the dominant effect is like when it's forward to the left, it's pushing all those air up a lot more. So it's just kind of dominating, I guess.
Okay. Several ways to think about it. One way is to think mathematically, like what you just did. Remember the flow field around the vortex, right? How does the velocity depend on the radius? Huh? 1 over r, right? 1 over r, okay? So the flow field in between this is the summation of two 1 over r functions. One goes like this, one goes like this. And if you go to decimals and just add up two functions, just the one is 1 over, let's say 1 minus r, 1 minus x, right? That's what we have to do. And another one is 1 over, no, plus 1 over, in this case, 1 plus x, right? That's well, just ignore the two sides. So these are like outside the vortices. Just look at here. It's actually the induced flow field. That's the contribution of the from the vortices, right? Is actually the minimum in the middle, and as you get closer to either vortex, it increases. Right? That's basically typically a summation of two 1 over r functions. You know, like at the vortices, there are singularities. The velocity, the acceleration due to these vortices are infinite when you get to here or here. And in the middle, when you are equally far away from the vortices, you still get acceleration, but it's actually the smallest. All right? Good? So that means the stream tubes and the velocity is higher over here. Higher velocity means narrower stream tubes. And narrower stream tubes on the two sides means the particle starting at quarter height is going to be closer to the center or the boundary. Boundary, right? Because at the boundary, the stream tubes are narrower due to higher velocity. Of course, you can also think physically, right? What force is accelerating? What force is providing? Okay, so let me ask. Start from more basic. So what is the flow acceleration at a point over here? Upwards, right? So there is no streamwise acceleration because of the symmetry, right? When the flow is achieves actually along the stream tube, it achieves the maximum velocity over here. Okay, so there is no horizontal acceleration. The only acceleration is the centripetal acceleration towards up. Now, what does that mean? What force provides that acceleration? What force provides the force for that needed for that upwards acceleration? Pressure gradient. I mean, that's the only force in the in the inviscid flow field, right? Only force. Pressure gradient. So that means at this point, is the pressure higher above or higher below? Higher below, right? How about this point when the flow is curving downward? It's higher above, right? So that means the pressure along this line is highest at the center and lowest towards the vortices. Now use Bernoulli, right? If the pressure is highest over here along this line, then it's slowest at here along this line. That means it's faster over here. That means the stream tubes are narrower. That means that quarter height particle is going to end up closer to the wall again. All right. I mean, this is basically how you see air, right? You use a chain of reasonings through physics. Not actually, I mean, at some point when you do that enough, you gain intuition, right? But you start not by intuitively think, but by reason. Like, how the flow field is actually doing. All right, make sense? Any additional questions on this flow field? Now we have two vortices. Okay, how about we switch the position of the two vortices? We make this 370 and make this 360, maybe 350. Now, what does the flow field look like? Yeah, it's like a cylinder in the middle, right? So that is starting to look like the flow around the solid object that's symmetric. All right. So basically we can play with all kinds of stuff, and here you can see stagnation point, right? Pressure is highest, and pressure is the lowest on the two up and down the two sides, right? Because the stream tubes are the narrowest. And you can get various. I mean, here what is the total force on the object? It's actually going to be 0, right? Because the pressure, as you can see, the velocity is symmetrically distributed left or right, and up and down. So the force would be equal to the pressure would be symmetric up and down and left and right. There is no force on the object. Okay, so yeah, so that's actually. When these two vortices are infinitely close, this is going to be exactly a circle, exactly a cylinder, and that's how you get the analytical solution for potential flow around a circular cylinder. All right. So, what are the basic building blocks? We have seen two, right? First, the basic building block is just the uniform velocity. U is equal to U infinity, V is equal to V infinity. That's almost a trivial solution, but when you add it together with other stuff, it's no longer going to be trivial anymore. And second is the vertical flow. We have seen it, right? U is equal to minus gamma over 2 pi. So gamma is the circulation of that vortex. Y over x squared plus y squared, and V is equal to positive gamma over 2 pi x over x squared plus y squared. That's the vortex we have been adding. And if you guys read the JavaScript code, you can just press F12 on that web page, and I think you can see the code that's actually computing the flow field by adding these vortices. So here I'm going to introduce a third building block, and that's all, right? The basic building blocks of incompressible potential flow are just the three things. So that's called that's uniform, that's a vortex, and the third one is called the source, and when the value is negative, it's called the sink. Okay, so it's basically a flow that's, when it's a source, it's basically a flow field that spews flow out of a single point. When it's a sink, it basically sucks flow into a single point, right? Both 2 and 3 are what's called the singularities. So basically, at the center, the flow is infinite and non-physical, but you use this to build the flow around it, right? At basically, you put these singularities inside the solid body, inside which you don't need physical flows, and you can construct physical flow fields outside. So here, U is equal to, well, again, S, the size, I mean the strength of the source over 2 pi, but X divided by x squared plus y squared. And V is equal to S over 2 pi, Y over x squared plus y squared. I'm not going to go through the math, but the math is pretty much the same as for vortex. That proves that the vorticity is equal to 0, and also the divergence is equal to 0. right? So basically, both satisfies the incompressibility condition and potential flow condition, which means it's irrotational, right? Zero vorticity. All right. Okay, so what is the source like? So let's just delete one of these and make the other one a source. This is actually minus 100, so it's a sink. So here we see what the flow field is like around the sink, right? It just sucks all the stuff in, and nothing comes out. Of course, if you draw a control volume just around this sink, you are gonna see mass just disappears inside it, and you are not satisfying the mass conservation equation. But if you draw any control volume that does not include that single point, like all the equations are satisfied. All right. And again, you see the velocity increases like what as you go towards the center, right? How does the velocity depend on how close you are to the source or sink? 1 over r squared? Just 1 over r, right? Because there is r squared over here, but you have x and y in the numerator, so it's going to be the same as for the vortex case. So the velocity, the only difference is that for the vortex, the velocity it induces is circumferential velocity, and for the source or sink, the velocity it induces is a radial velocity, right? And let me just make it positive to see what the source is like. So just spews flow out of this singular point. All right, and if you add it together with a free stream, it basically simulates a solid body. Let me actually put the y location to be exactly along a streamline that comes over here. So 360 is half of the height of the canvas. So I mean, there is a particle that goes directly towards it. So as you can see, as the particles start to approach this point, you're going to see that what they simulate, it's actually similar to the leading edge of an airfoil, right? So these actually provides what the contour is like for a solid body that encompasses that source, right? And all the flow field that doesn't include this point is valid. So if you have a solid body that has this contour, then you would have a flow field around that solid body that's completely valid outside. And again, as you can move the mouse and see, the velocity as you get closer to the stagnation point is pretty much zero, right? I mean, I don't know if you can see it over here. The pressure is stagnation pressure 0.5. And as you go around it, like as you go towards here, the pressure becomes negative, which means the velocity is higher than free stream, right? Positive pressure means just according to Bernoulli, means the velocity is slower than free stream. Negative pressure means the velocity is higher than free stream. And then as you go more downward, the pressure kind of recovers. It's still negative, but starts to get closer to zero, right? I mean, at some point, you get a minimum of pressure, maximum suction, like over here, So that's how the flow field is like around the leading edge of a symmetric airfoil. And of course, you can move this upstream a little bit. Let's move it here. And if you duplicate and make a source of, let's say, negative 50, and duplicate it even further more and make it downstream and make it further downstream, right? So I'm basically giving a source upstream and 2 sinks downstream that actually exactly balances it. So basically the total flow that spews out of the source per second is equal to the sum of the flow that's sucked into these 2 sinks. per second. What's going to happen is that you can already see I have a stagnation point, right? And I have a solid body that it's not a trailing edge yet because it's not sharp, but at least it starts to resemble like an airfoil, right? So that's what could happen. Actually, one thing that's actually very interesting is that if you make a sink that's very close to it, so let's, instead of further downstream, you make it a little bit downstream, you get exactly the same effect as placing two vortices up and down. It's again the flow around the circular cylinder. And this is something you can mathematically prove, is that similar to what you are doing in your second homework, right? You can prove that if you make this source and sink closer and closer to each other while increasing their strength, you are going to actually converge to exactly the same flow field as if you place two vortices opposing each other and make them closer while increasing their strength. That limit flow field is, we can think about it as a compound of either two vortices or two sources. I mean, one source, one sink. It's called a doublet because it doubles. Anyway, that's called a doublet. And this is pretty close to the flow around the doublet. All right, any additional questions over here? So other things like a doublet is a compound. Doublet can be obtained by multiple vortices, by just the two, right? I mean, other things people also used to build can be obtained by more than two, or a source and a sink. All right, that's basically the building blocks. I mean, in this class, we're just going to be using free stream, vortex, and source sinks. We're not going to be using doublets and more advanced stuff. All right. Okay. So let me ask you another example. Can you actually see air? In the vicinity of a corner, the flow, assuming no boundary layer and stuff, can be described as U equal to minus X, V equal to 1. Think about what the flow field is. Now consider an element at point P, all right, which at t equal to 0 has the shape of a rectangle. What do you think the shape is going to be like a short time later?
It'll be a little more compressed.
It'll be a bit more compressed, like in what way?
The stream field widens as it moves along, so that it's going slower, which means the pressure is higher.
Yes. Yes. That's right. The pressure is higher, so, and remember we are looking at incompressible flow, right? So if you take the du dx plus dv dy, that actually tells you if it's compressible or not. Like if the du dx plus dv dy is not equal to 0, that means the density has to change along the streamline. Then it's compressible. But here, du dx is equal to minus 1, dv dy is equal to plus 1. So it's incompressible flow, right? So the pressure does increase over here because the stream tube widens, but the density density doesn't change because the flow velocity is so small and compared to the speed of sound. And also, what is the vorticity here? Zero, right? Because du dy is equal to 0, dv dx is also equal to 0. So du dy is equal to dv dx. Okay, so we can use Bernoulli. That just means we can use Bernoulli across streamlines. And the flow is a composition of, the flow can be approximated at least as a composition of the basic elements. Okay, any additional ideas on how this is going to change its shape? Yes? Yes, vorticity is 0, right? So it's going to stay as a rectangle. Let's actually try it again in the flow builder. So this, how would you construct the basic elements to get a flow field like that? One vortex? Where?
Like top left, that little like box right there.
Remember, you need the 0 velocity over here. Like when x and y are equal to 0, you need 0 velocity. Any ideas about how I should construct the flow field, how manipulate this to get the flow field like that? I put a doublet in the corner. This is already a doublet, right? Where do you? Oh, okay. So you are saying this corner is very much like it. So let's just make it bigger, and I actually don't need the sink, right? If I have a source, it's already bigger, right? So this actually resembles that flow field even a little bit more, right? Okay, so let's actually make it more visible by moving it downstream a little bit. So maybe make it over here. And we are going to actually not just rely on a single source. We are going to make a wall of sources. We are going to duplicate it for 5 times and change the y. So I will start with 160. I'll do 260, 360, 460, and 560. Oh, I think I need to make the strength a little bit lower. So because okay. So now I have a wall, right? I can further duplicate it to make it even a higher wall. 760. I'm also going to duplicate these to make it 60 and minus 40. Minus 40. Okay. So now I really have a wall of sources that keeps spewing stuff, right? I mean, theoretically, you can show that if I have an infinite wall of sources and the spacing between the sources are small, okay, if I have an infinite wall if you have infinite and continuous wall of vortices, then you get exactly that flow field we are describing mathematically. Here, it's actually pretty close because it takes a long time for this to get to equilibrium. But if you look at the flow field, right? U is basically goes linearly when x is if x exceeds this stagnation point, U becomes positive. If x is upstream, U becomes as x becomes downstream, U becomes negative. As I go upstream, we get a positive U. Similar to V. If I go upper, V is positive. If I go lower, V is negative. Right? It's pretty much that flow field. And what we can do is we can actually, if you click on this, you get a rectangle of particles, and you can watch how it's going to be advected downstream. All right. So we can see what happens. Initially, it's a square of particles, and now it's already deformed into a rectangle, right? This is because the x velocity decreases as you're approaching the stagnation point, right? So the stream tubes widen. Imagine the upper and lower thresholds of the originally square is the bounds of two streamlines, right? Then as the streamlines widen, this gets stretched. While at the same time, we have conservation of mass. So the total area of that rectangle would not change, right? That's because the area is proportional to how much mass is within that control volume, essentially. So this square now get stretched into a very elongated rectangle. All right. Yes?
Just explain one more time.
Oh, why it's elongated? Because so let's imagine I see the square over here, right? The upper and lower bounds of the square are exactly the boundary of two streamlines. Okay, this streamline, as you go downstream, widens because because the velocity just decreases, right? So it has to be pulled apart on the top and lower parts. While at the same time, we have conservation of mass, so on the x direction, it has to be squeezed. All right, make sense?
Yep.
Any additional questions? Right, this is what happens on the leading edge if you really zoom in, right? So we are basically zooming into a stagnation flow, and in the stagnation flow, this is actually the velocity field. If you zoom in enough, so that you cannot even see the curvature of the leading edge of the airfoil, right? That's really what happens. Okay, and this is actually the basics of the flow field, as we will discuss later when we look at the boundary layer, for example, that forms at the leading edge. So we'll reuse that inviscid flow solution to discuss how the boundary layer forms at the stagnation point of an airfoil. But that's several weeks later when we are discussing viscous flows. All right. What if you have the same flow but a rectangle that's skewed? What do you think is going to happen to the flow? To this rectangle? It still gets stretched, but in what direction? Would it stay a rectangle?
I think it would all be probably. The corners are going to pull like that.
Exactly. Let's also try it. So when you click on it, I don't know if I have luck or not, but like I think it randomly. Yeah. Okay. So this is a diamond, right? And we can see how this is going to deform. One of the things is that this is a irrotational flow field, right? But irrotational flow field does not mean that a rectangle is going to stay a rectangle, because it can deform into a diamond. Irrotational just means if one edge rotates in one way, the orthogonal edge is going to rotate the other way, right? You just cannot have two orthogonal edges rotating the same way. That's not allowed in the irrotational flow field. So you can see as this diamond gets squeezed, the originally edge that's pointing towards the towards the positive x, positive y direction gets rotating in a counterclockwise direction, and the orthogonal edge gets rotated in a clockwise direction. So you get a thin diamond at the end. All right, you can play with this kind of stuff. I mean, I can play with this all day long. So if that happens to you, I'm sorry for wasting your time. Okay, so we'll skip that. Maybe to end this, I'll start to provide you a counterexample, right, of the sum of steady-state flow fields actually doesn't have to be a steady-state flow field. And here, I'm going to use one irrotational flow field and one rotational flow field, right? Similar to, I think, what one of you have, who posed the potential counterexample for compressible and incompressible flow. You, right? So this is very similar to your spirit. So one flow field is the source. That's U is equal to, let me just say, x over x squared plus y squared. V is equal to, let's say, the first flow field, y divided by x squared plus y squared. And the other one is a rotation, but not a vortex, but actually a rotation. Okay, so that's U would be equal to minus y, and V would be equal to plus x. Right? Remember when we are constructing flow field that has a circular streamlines, this is one of the solutions. This is one of the solutions that are rotational, not irrotational. Because du dy is equal to minus 1, dv dx is equal to plus 1. So the vorticity, if you subtract them, it'll be 2, right? Okay. Now if you add the two flow fields, of course mathematically you can show that you cannot find any pressure field that would actually satisfy the conservation of momentum equation. You can find one pressure field that satisfies one conservation of momentum equation, but then that pressure field is going to violate the second conservation of momentum equation in the other direction, right? More physically, we can also show it through this flow field not satisfying the conservation of angular momentum. So what happens is that we have this origin that spews fluid outwards, right? So basically we have fluid that spews outward from it. And as the flow goes towards higher and higher radius, it automatically gains more angular momentum just out of magic. All right, and there is no, the pressure field, right, being a conservative, the pressure force is a conservative force because it's proportional to the gradient, right? So it cannot provide a torque to the flow field. If you integrate the pressure gradient over a circular path, the total integral of the pressure gradient along that contour direction has to be equal to 0, right? Because you are integrating the gradient of a scalar, right, along the circular path. So that means the pressure cannot torque the flow, and yet as the flow expands outwards, it is gaining more angular momentum. That means this cannot happen in the real world. All right. So basically, the answer to this question is generally no, right? Especially as you go outside of this ideal scenario of incompressible and a potential flow. You should not add two flow fields and assume it's another valid flow field. We can only do that if we have incompressible potential flow. All right. Okay, so we have several minutes left, and let me start by actually going a little bit in the aerodynamic shape and lift. So we'll try to do something like this, right? We'll basically go and type a NACA airfoil. So it's actually a lot less time consuming to build fat airfoil. So like I think what I did was NACA 0032. So I think in Unified you all learned this NACA airfoil designation, right? The first two digits are the camber, like basically how the airfoil is non-symmetric, and the later two digits are the thickness to chord ratio. So 32 means the thickness is 32% of this chord length. If the structure is more important than aerodynamics, but you still want some aerodynamic consideration, something like this is a perfectly valid design on the airplane. All right, because this is it is thick enough for bending moments and things like that, but still reasonably aerodynamic. Okay, so placing sources now. Let me get rid of all of these. It's much better to place sources along the center line and upstream, right? So let's just try over here. And we can see that, okay, this roughly gets you here, but we want something that's even thicker, right? So we increase the strength of the source. And see now this point actually probably too thick. So we scale back a little bit, maybe 60. That gives you, do you think it's still too thick? That's the stagnation point, right? We can see the flow going that way. Maybe 50 is fine. Okay, and then we move it upstream a little bit so that we get the stagnation point. Maybe 50. That kind of matches the stagnation point of the airfoil. Okay. Of course, we have to duplicate it to make a negative 50 at a downstream location. So let's say 940. That gives you a sink downstream. And then you're gonna see that the shape doesn't really match. So we probably want to duplicate another source at some point, but maybe downstream over here. That I think should have the contour of the airfoil at least near the leading edge matched pretty well, right? But then, of course, we want to duplicate and make a sink someplace later. This might be too much downstream, so maybe over here. So you can see that I'm already having this part of the airfoil sketched out, right? It comes, there is a little bit mismatch, but we start to get something that resembles this part of the airfoil. Of course, then you also have to place the sinks to get this shrinking nicely downstream. But once you're able to do that, we can really interrogate the whole flow field to get all the pressure distribution, right? Of course, here you get stagnation pressure 0.5, and over here you get a pretty big suction, right? You all know like the pressure coefficient CP, right? The CP is basically this value divided by the stagnation pressure divided by half. So here you get a CP of minus 0.6. And over here, the pressure would recover, right? The CP is less negative. And well, if you follow the contour of this at the downstream location, the CP becomes positive again. So this is really at the trailing edge, you get a recover of pressure. So this is something we'll start doing next lecture. All right, so we'll basically be looking at how you would place source and sinks and the vortices to approximate airfoils of different shape, and how do the placement relate to exactly what the shape of the airfoil look like. All right, see you Wednesday.
I